Lamb's quarter is a common weed that interferes with the growth of corn. An agriculture researcher planted corn at the same rate in 16 small plots of ground and then weeded the plots by hand to allow a fixed number of lamb quartz plants to grow in each meter of corn row. The decision of how many of these plants to leave in each plot was made at random. No other weeds were allowed to grow. Here are the yields of corn bushels per acre in each of the plots. So here's the data that we were able to get, right? A scatter plot of the data with the least squared line added to it is shown below. Describe what this graph tells you about the relationship between these two variables. All right, so we can see that there's definitely at least a negative, probably weak linear, right? So the scatter plot suggests that there is a somewhat weak negative linear relationship between the number of weeks per meter and the corn yield of the plots, right? So relatively weak, we're going to see how weak it actually is. So here's the data that's Minitab output, right? So from this, what is the equation of the least squares regression line for predicting corn yield from the number of lamb's quarter plants per meter? Define any variable you use. So right off the bat, I know this is my constant in my linear regression, and this is my slope, right? So let's go here. So the equation is going to be y hat is equal to 166.483, right? Minus 1.0987x, right? Where, of course, y hat is the predicted corn yield and x is the number of weeds per meter, all right? So from the Minitab output, that's how we're able to get that. And they're telling us that r squared is 0.209, right? So r squared is equal to 0.209. So this implies that r, remember this is the correlation coefficient, is equal to the square root of 0.209. And then I'm going to use the calculator in order to get all of this stuff that we got from the Minitab, right? So as you can see, I put in all the data from my set there. And what I'm going to do here is I'm going to go to Menu, Statistics, Stat Calculation, and I want the linear regression with A plus BX because this is the model that I have it in, right? So my X list is going to be those weeds, right? And then my Y list is going to be the corn. Okay, so let's go ahead and put that there. So as you can see, I have that 166.483 for my constant, right? And for my slope, I have the negative 1.09872. R squared was that 0.209. And of course, when I take the square root of r squared, it'll be plus or minus this, right? But since this was negative, it's going to be negative 0.457. So negative 0.457, right? So this tells us that it is a negative linear relationship, but it is really weak, right? Because it's not close to -1, right? So this sort of justifies what we were saying earlier in the problem. All right, so let's go ahead and do C. Interpret the slope and y-intercepts of the regression line in context. So the y-intercept says that if there are no weeds per meter, we would predict a corn yield of 166.483, right? That's when we have 0, right? Right? If we were to have 0 weeds, we'd have a yield of 166.483. And as we introduce more weeds into the plot, the yield will reduce, right? The corn yield will reduce. The slope says that for each additional weed per meter, we can expect the average corn yield to decrease by 1.0987 bushels, right? Okay, so D, do these data provide convincing evidence that more weeds reduce corn yield? Carry out an appropriate test at the alpha equals 0.05 level to help answer this question. All right, so we want to perform a test of, so the null hypothesis is that the slope, the actual slope, that's what beta represents, right? The actual slope is 0, so introducing the weeds won't have a negative impact on the corn yield, versus, of course, the alternate hypothesis saying that if we were to introduce the weeds into the corn, our yield would be less, right? Where beta is the true slope of the population regression line relating to weeds per meter to corn yield, and we will use alpha equals 0.05 because I believe that's what it says to do here, right? All right, so from our data we got here, what we can do is we can get these values, right, for our regression line. So let's go ahead and label this regression, right? And then the function we're going to have is 166.483 minus 1.09872, and then it's going to be weeds, right? Weeds. Okay, so when I click enter, right, this is going to give me all the predicted values for my weeds, right, from my regression function, right? Okay, so now what I can do is I can get my residuals. So I'll do RES for residuals, and then that's just going to be, so it's going to be my actual values minus my regression values, right? So residuals is going to be A minus E, right? So let's go ahead and do that. So these are the values of my residuals. So that's the difference between the actual values minus the predicted values I got here. Okay, so now we're going to get a quick graph of our regression line. So we're going to go to menu. We're going to go to data. We're going to go to quick graph. And what we're going to do is we're going to do our weeds down here for X and our corn for our Y, right? Okay, so hopefully you guys can see that. Now what we're going to do is we're going to go to menu. Okay, so we'll go to analyze, and we'll go to regression, and we'll go to show linear. So as you can see, there's our linear line. All right, so what we can do now is we can form a residual line. Plot, and we can have a residual, so show residual plot. So as you can see, we have our residual plot here, and it looks pretty randomly scattered, right? Which is a good sign for linearity. Okay, so there's our data here, right? So we can talk about it a little bit. So let me scoot it down a little bit. So the scatter plot is approximately linear, right? The scatter plot is approximately linear. Also, the residual plot shows a random scatter of points about the residual equals 0 line. See that residual equals 0 line? There's a scatter of points, right? A random scatter of points. So this is a good sign for linearity, right? Now, independence. This was a randomized experiment. Due to random assignment, the observations can be viewed as independent, okay? So now the normal, we're going to find our X bar for our regression, our standard deviation for our regression, and so on. Now we want the one variable statistics for our residuals, right? So let's go ahead and go to menu, statistics, stat calculator, and one variable statistics. We want it from F to G, or we can name this residual, right? Doesn't matter. Residual to G, and there's going to be our one variable statistics for our residuals. Okay, as you can see, I filled out the information here. So let's go ahead and go to our outlier test. So Q1R, is negative 5.89. It's going to be minus 1.5 times 6 minus negative 5.89. And that's going to give us a negative 23.7, which is less than our minimum for our residuals, right? The other one is going to be 6 plus 1.5 times 6 minus negative 5.89, which is equal to 23.84, which is bigger than our max for R. So there are no outliers for our residuals, right? Okay, so now let's check for skewness in this data. So first off, we know that X bar for the residuals is, so it's going to be less than the minimum, right? Or the median, less than the median. So this implies there's left skewness, right? So left skewness. But we're going to see if this is significant or not. We can clearly see it's not going to be really significant because that difference is minuscule compared to the standard deviation, right? But let's go ahead and do this. So we know this is going to be equal to 0.0003 minus 0.5 times that 7.71. And then 0.0003 plus 0.5 times 7.71, which this will give us the interval negative 3.85 to positive 3.85. And we know that the median, which is equal to that 0.52, right, is an element of this interval, right? Negative 3.85 to 3.85. So this implies that there's only slight left skewness. So that means the residual distribution is approximately normal and we're good, right? Okay, so the next we need is equal variance, right? So what I put here is the residual plot shows roughly equal scatter for all x values. And you can see that in our plot here, right? The scatter for these are about equal, right? So there's equal variance in our residual plot. Okay? And of course, the last condition, random, this was a randomized experiment. So the conditions are in fact met. So let's go ahead and do our hypothesis test. So the T star actually comes from up here. See, I have T is negative 1.92. So that's where I got that. And our degrees of freedom in these types of problems is going to be the number in the sample minus 2, which is 14. So let's go ahead and go to our table. Okay, so here's our table, our T distribution table. And it's going to be, of course, this is the positive and we're looking for the negative, but it's symmetric, so we're good. So we're going to look at degrees of freedom, and 1.92 is between 1.71 and this one here. So the p-value is going to be between 0.025 and 0.05. We know the p-value, so the p-value is going to be 0.025 less than p-value. P-value is going to be in between these two values, right? So we can see the p-value is less than 0.05. So since the p-value is less than alpha, which is 0.05, we reject the null hypothesis that stated that the true slope was equal to 0. And we conclude that there is convincing evidence of a negative linear relationship, which, of course, we saw throughout this problem, right? Even at the very beginning, we saw this negative linear relationship. So we have indeed shown through a hypothesis test that this data does have a negative linear relationship.